day. We are doing a presentation about the analysis on the impact of urbanization and low-impact development at Barangay Malawin, Orani, Bataan using SWM 5.1. And the presenters are myself, Vianney Luigin Santos, Chelsea Gorospe, Jessel Manyo, Patrick Jason Felicilda, Jefferson Galasi, and Robert Jun Tagle. This presentation includes the introduction, methodology, results and discussion, and recommendation. The diminishing in the reasonable land territory for invasion of the encouraged water due to, for example, land use is one of the primary supporters of expanded overflow volume and issues in stormwater the board. The regular stockpiling vehicles for these hazard waters, for example, vegetative zones, subsurface, soils, snowpack, and water bodies are being risked because of the relative multitude of exercises coordinated to human use and abuse. This is the map of Barangay Mulawin, Orani, Bataan, and the black line here is the site study we use for simulation of SWM. We have here the rain gauge, the subcatchment, and the broken line here is where the water will flow down to the river. From here, we have the junction 1, catchment, and outfall. The rainfall that falls in the subcatchment will flow to the drainage, then to junction, and then to the catchment, where it will have less and cleaner volume of water before it reaches the outfall. This is how low-impact development works.
Methodology. The province of Bataan has been chosen as the study's location. Bataan is vulnerable to typhoons and other weather disturbances, such as Sabagat in the southwest monsoon, because it is a peninsula. Furthermore, the clogged drainages and silted waterways, as well as the ongoing conversion of former agricultural land to commercial areas, have been identified as factors contributing to local flooding in the province. The case study area, according to Barangay Mulawin's present land use plan, is mostly residential land with few commercial and institutional structures thrown in for good measure. Mulawin is located on the island of Luzon at around 14.7974 degrees north, 120.5020 degrees east. At these coordinates, the elevation is approximated to be 5.1 meters or 16.7 feet above sea level. Mulawin is a barangay located at Municipality of Arani, Province of Bataan. As per the 2015 census, there were 4,380 individuals residing there. These accounted to 6.55% of Orani's overall population.
These are the parameters of our simulation. Subcatchment parameter. Area is 8 hectares. Width of overland flow path is 500 meters. Average surface slope is 0.5%. Imperviousness is 50%. Conduit parameter is shape of cross-section is circular. Maximum depth of cross-section is 1 meter. Length of the conduit is 600 meters. Roughness of the cement is 0.015. We've used two different LID, which are the rain garden and rain barrel. The parameter of soil thickness of the rain garden is 100 millimeters, while the rain barrel, its height is 1,000 millimeters.
Scenario 1, effect of percent imperviousness using 90th percentile without LID. Scenario 2, effect of individual LID on varying percentage imperviousness using 90th percentile. Scenario 3, effect of combined LID of varying percentage area covered using 90th percentile. Phase runoff coefficient, and final storage show positive linear relationship to the increasing imperviousness, while the infiltration losses show otherwise. So sa scenario 1, makikita niyo yung graph. Ayun yung graph ng effect of percentage imperviousness using 90th percentile without LID. Tapos sa may bandang right side naman, makikita niyo yung table. Yung table na yan, As you can see sa table, ang imperviousness is tumataas every 5 years. 50%, and then after 5 years, magiging 75%. And then after 10 years, magiging 100%. Sa table, makikita mo na habang tumatagal or habang tumataas yung percentage, mas tumataas din yung surface runoff niya. And then yung mga natitira na nasa table, which is total precipitation, runoff coefficient, and infiltration loss, makikita mo siya once na nirun mo na yung software niya. So sa scenario 2 naman, ganun din. Kaya lang, mayroon kaming dalawang pinili na LID. We have rain garden and rain barrel. Ganun din naman yung imperviousness niya, which is 50%, 75%, and then 100% na tumataas every 5 years din. Malalaman natin dito kung effective ba yung ginamit namin. Sa rain garden, kapag ang imperviousness niya is 100%, makikita mo dyan sa table na yung surface runoff niya is 5.21. Mababa, which means nagwo-work siya. While yung rain barrel naman, ganun din, kapag tumataas yung imperviousness niya, mas tumataas din yung surface runoff niya. Ayan yung significant difference ng iba't ibang LID kapag in-apply siya sa simulation. Pero yung napili namin na dalawang LID is rain barrel and rain garden.
Scenario 3. Effect of combined low impact development on varying percent area covered using 98th percentile. Low impact development control. Rain garden at 0.3A and rain barrel at 0.2A. Imperviousness percent, 50%. Total precipitation, 17.40 mm. Surface runoff, 7.27 mm. Runoff coefficient, 0.418. Infiltration loss, 1.42. In scenario 3, the subcatchment was simulated at varying percent imperviousness at 50% imperviousness, which represents the present state of the subcatchment area, at 75% imperviousness representing the influence of urbanization on the site, and at 100 imperviousness representing the absence of green landscape on the site. And shown in this table is the summary of the results obtained from the analysis of the model, which shows that the surface runoff coefficient, and final storage have positive linear relationship to the increasing imperviousness, while the infiltration loss show otherwise.
Recommendation for a research catchment in Barangay Mulawin, Orani, Bataan, a subcatchment scale swim model capable of estimating actual runoff quantities was created. The model was calibrated using information from the port area rain gauge. The simulation found that using a catchment with LED controls spanning 100% of its area resulted in the lowest surface runoff, with an efficiency difference of 86% when assessed at 100% imperviousness, and 78% when tested at 50% imperviousness. Furthermore, in different simulation scenarios, rain garden exceeds the other LED controls utilized in this research in terms of managing water quantity. However, the researchers advised that additional data efficiency be conducted to extract reliable and significant analysis. Other potential LID controls or combination of LID must be also investigated to determine their effect on runoff characteristics. Lastly, when selecting an appropriate LID control, the cost of operation and maintenance must be taken into consideration.